Welcome to our presentation on our network for a network science course. And my name is Said, and with the three other teammates, Nazik, Summer, and Doyan, we worked on the airport network. And I'm going to talk you through about like motivation, and Nazik is going to talk about the data collection and network definition, and my colleague Doyan talk is going to talk about methodology, and we're going to talk about results, and then conclude and the conclusion. So the motivation. I think I was the person who came up with the idea, and I'm really fascinated by the aviation industry and the airlines, the way they work actually, and the way they change our our world and the globalization. So I found it very interesting to check it out and how it works out because I knew about the small world phenomenon that you can connect any person in the world with only like less than 6 hops, and I wanted to implement a similar thing to an airport network. If we can travel from one airport to another random airports in the world, and we wanted to analyze that, see if that's possible, any random airport, and how they are connected with each other, and also what happens when we have some failures at some hubs, let's say the big airports, that can happen in nowadays as well, that some airports have to close because of the bad weather or something, and how does that affect our air travel? So yeah, that's why we're gonna focus on like the small world verification. If the small world is firstly, yeah, available, if it's there, if it exists, and then the topological analysis, and then lastly the robustness evaluation, which I just said. When a hub fails, what happens then next? Okay, so Nazik is gonna talk about the data we collected.
So, hi everybody. We, for our study, used actually the publicly available OpenFlight datasets, which includes information about almost 7,000 airports and like 70,000 additional information about the routes, airlines, countries, and other metadata. In order to improve the coverage, we extended the dataset through an API queries where we added missing routes to reduce the number of isolated airports, and we succeeded reducing that by almost 24%. So our final airport network contains of 7,600 and 98 nodes or airports and about almost 20,000 edges. And that is actually forming the basis for the subsequent analysis. So starting by the airport level network, as said, it's our fundamental representation where each airport is a node and each direct flight route is an edge. So in this way, we have like a detailed view that captures the actual complexity of the global travel and serve as like starting point for building aggregated networks at country, airline, and community levels. So from the airport network, we derived, go back please.
Sorry.
We derived the three higher level representation, the airline level network that reveals how like individual carriers structure their operations, the community detected networks that uses an algorithm to identify naturally occurring clusters based on connection patterns, and the country level network that groups airports by nation to analyze like the international connectivity at higher scale. Then, in the country level network, each node represents a country, a state, and each exists between two countries, if and only if there is at least one direct flight between any of their airports. So, in this view, we like excluded domestic routes. So we focus on international connections, resulting in an undirect weighted graph where each weight reflects the number of airport level routes between country pairs. And next one. Yeah, we can like see some examples there. Some country like pairs show a strong connection. For example, the UK and Spain, they share almost 1,000 direct routes. The US and Mexico, almost 700 direct routes, and the US and Canada, almost also 700 routes. So these high weight edges reflect deep economic integration and let's say, the high volumes of passengers traffic, we can say. Now, in the community detected network, we used a Leuven algorithm, if I'm spelling it correctly. And so we identified groups of airports that are more densely connected internally. Not surprisingly, these communities align strongly with geographic regions. For instance, we found out that the largest community is the North American, the second largest the Asian, and the third the Oceanic. Now,
All right, then in this section, I'll briefly introduce our methods used in our study. So our analysis focuses on four main parts: small word confirmation, topological characterization, robustness analysis, and community detection. So importantly, we apply the same method to various kinds of network, and then we made a consistent comparison across different aggregation scales. So first, we examine whether the air transportation network exhibits small word characteristics. All analyses are performed on the largest connected component to ensure that path-based measures were well defined. For each network, we compute the average clustering coefficient. So for each network, we compute the average clustering coefficient, which captures local clustering and the average shortest path length. And also to determine whether these properties indicate a true small word structure, we compare the result with ER random graphs that have the same number of nodes and edges. So this allows us to check whether the networks simultaneously show high clustering and short path length. And then next page. And then next, we characterize the structure topology of each network. At the network level, we compute basic metrics such as the number of nodes and edge, average degree, and network density to describe overall connectivity. To examine heterogeneity, we analyze degree contributions to identify hub-like structures. And also, in addition, we compute degree, betweenness, and closeness centrality to evaluate node importance from different structure perspectives. We then evaluate network robustness by analyzing how connectivity changes under node removal. We consider two strategies: random removal, which simulates random failures, and targeted removal, where nodes were removed based on degree or betweenness centrality. After each removal step, we measure the size of largest connected components, the number of connected components, as well as changes in path length and network diameter. In addition to global and node level analysis, we apply community detection to identify mesoscopic structures in the network. We use the Louvain algorithm because it scales well to large networks, does not require a predefined number of communities, and is widely used in transportation network studies. The algorithm detects communities by maximizing modularity. We apply this method to the airport level network and analyze the detected communities using the same metrics as in the other analysis.
So I'll continue with the results. So what we found out in our studies actually, that the airport level network is indeed a small word, with an average shortest path of length of 4.33, and the average degree is equal to 5.16, meaning that in our network, each airport connects to about 5 others on average. The network itself is actually weakly associative, and the centrality analysis confirmed that we do have like major international hubs, like let's say Frankfurt, and they play dominant roles in global connectivity. If we look into at the airline operations, we found actually that we have like major carriers like Ryanair and American Airlines, where each operate over about like 1,200 routes. Under a scenario where we just 5% of the airports are randomly removed, the network airlines, such as like Lufthansa or Air France, lose more than 10% of their routes. And that's actually highlighting their heavy dependence on hub connectivity and the shared infrastructure. So regarding the robustness, we found out that the airport network shows actually moderate robustness to random failure, but it also shows extreme fragility to targeted attacks. So random removal up to 10% of the airports preserves the local connectivity, but beyond that, fragmentation accelerates, meaning that the targeted removal of just about 4% of the airports, so those with high betweenness, causes the most rapid collapse of the global connectivity and the shortest path efficiency. And that is actually applied to all other targeted attacks.
So at the country level, we have we talked about the network before, that how countries are connected with each other and ignoring the domestic routes. We saw that there's an average shortest span of 2.332, and the average degree was like 20.74, which means that there's on average like 20 countries that are connected with one country on average. So the degree distribution was highly skewed, so indicating that there's a strong hub dominance. And the centrality analysis showed that the major hub countries are dominant, like France or like the US. They have they are dominating the network in a sense. And then between the centrality shows that also countries like intermediary are in the shortest path, like the UAE or the Australia. They're like in the middle of the shortest path, mostly making the shortest path, being in the middle. And then the robustness analysis is that we removed we performed a random node removal, and with this one, the LCC retained still over like 90%. Even after 60% of random removal, both like local and global connectivity was preserved. When it comes to degree-based targeted attacks, they reveal the vulnerabilities much better, because like we said, it's like very hub dominated. So once these hubs or like the high degree nodes, the airports are attacked, removed, failed, this of course leads to significant fragmentation in the path length. And then lastly, the between the space attacks, they're the most destructive. Like if there's an airport shutdown in UAE or Australia, like these intermediate countries, then it degrades the global efficiency much sharper. And when it comes to community level, all 10 communities confirm like a small work behavior as well. They have the coefficient range from 0.26 to 0.44. So the average path length ranges from 2.6 to 5.1, which is still less than 6, which is needed for small work confirmation. Each top community exhibits a highly skewed degree distribution, similar to previous network, and major hub airports dominate within each region and play central roles, just like the previous one. Similar behavior in topology. When it comes to robustness analysis, the communities are resilient to random failures. They also with other networks, and they are not affected pretty much when it comes to random removals. However, when the hubs are targeted, when they were removed, there was a higher fragmentation we can see. But the community structure remains highly stable with consistent grouping, or even after 10% of edge removal. So they can still keep the community. And inter-community connections are especially fragile when it comes to removals. An analysis that only like 5% of bridge airports cut in the global efficiency by 80%. So this reveals a critical dependence on a small number of international hubs for connectivity.
Next part, and we compare airports versus country level networks to see if node importance persists under aggregation. I will go through small world structure, topology, and robustness. So first one is, sorry, next slide. Thank you. Both networks show smaller properties, but the country level has higher clustering and a shorter path because aggregation strengthens small world structure. And next, after aggregation, degree distribution is less extreme, but still heterogeneous, hub dominance persists. Degree centrality is preserved, while betweenness and closeness are more sensitive. And next part, robustness. Country level is more robust to random failures, but airport level collapses faster under targeted attacks. Aggregation smooths extreme vulnerabilities. And next part is the conclusion. First, we found that all networks level exhibit a small world structure with high clustering and short path. And second, hub-dominated topology is consistent also across all levels. Degree distributions are highly right-skewed with more different centrality measures reveal different roles. Degree identifies connectivity hubs like Frankfurt and France. Betweenness highlights bridge nodes. Australia have moderate degree but critical bridging roles between continents. And the next is like the networks are robust to random errors but fragile to targeted attacks. Under random node removal, the networks show higher robustness, but all networks are vulnerable to targeted disruptions. At the airport level, betweenness-based attacks are the most effective. The country-level network is more robust due to multi-airport redundancy, and inter-community connections are most vulnerable. And the last part is limitation. Our data set is a static snapshot from 2014. Some parts of airports remain isolated, and we use unweighted edges, ignoring flight frequency and capacity. What's more, our static analysis overlooks the three key dynamics. First one, real networks adapt through rerouting and partnership, so we may overestimate the vulnerability. Second is like seasonal variation affect route importance but aren't captured. The last one is like long-term evolution from mergers and strategy changes constantly reshape the structure. These limitations suggest maybe the real-world resilience may be higher due to the system's adaptive uh, sorry. These limitations suggest the real-world resilience may be higher due to the system adaptive capacity. That's our presentation. Thank you.
Thank you very much.